because this is the clue of my fit for the video. But you can't say it out loud, okay? You get bonus points if you get it by the end, okay? Do you understand? Try to remember that. And then I'm going to, if you need to go back, you can watch the video and pause it. But that's the clue for the clue and the fit are both clues to the key phrase that gets you bonus points on your test. Today, oh, I'm so sorry. Chemistry time. Today we are talking about light and quantized energy. Light and quantized energy. The objective is identify and quantify variables relating to light and quantized energy. So I'm going to write that down. Identify. So by the end of the video, we will have identified and something else. Quantify. We will have quantified. What does it mean to quantify something? Deal with it in the terms of numbers, yeah, all that. Yep, not just multiplying, but yes. Quantify variables relating to light and quantized energy. Variables relating to light and quantized. My shirt doesn't say anything. Energy. My shirt says nothing on it. It's just a white shirt. Light and quantized energy. And I'll do a little flourish and then we'll begin. Light and quantized energy. Okay, so I had asked you moments ago, learners, scholars, no response at all. I had asked you moments ago, scholars, what does it mean for something to be quantified? That's why I said, what does it mean if we quantify variables? And you said correctly, to deal with it in terms of numbers. And it's the same thing with quantized. Quantized is this idea that things can be broken into discrete. You need to be very specific with the way you spell this. Broken into discrete amounts. Okay, there are two different, this is a side note. This is an English language usage side note. This is a spelling and syntax, maybe not quite syntax, but Tommy, you need to pay attention. This is very important that you learn this in your life. There's a divide between discrete, spelled like that, and discrete, spelled like that. You see this one is D-I-S-C-R-E-T-E, and this one is D-I-S-C-R-E-E-T. There's a difference. The right one is this one, D-I-S-C-R-E-T-E. Discrete, spelled in this top way, or like it is in this sentence, means it can only be of a certain amount. So stairs are discrete. You can be on one stair or on the next stair, but you can't be between stairs. You can't like be hovering in between. Like, I mean, in real life, you could have 1 foot on one or 1 foot on the other. But the classic symbology of something being discrete is that it is one or the other and nothing in between. Okay? Discrete like this, as a side note, this is the side note, discrete like this means that it's sneaky. So if you're trying to be discrete, maybe you were trying to be discreet when you came home when the dance ends at 10 on homecoming, and you tried to be discreet coming home at 2 a.m. You're like, no, Mom, the dance lasted till 2 a.m. Sorry. That's so discreet. And also, like, if someone asks for your discretion, it means that they don't want you to tell a secret. They don't want to tell a secret. So these are, discrete, the way we're using it today, I want to make sure that I actually got this right. Trying to look for this word. I don't actually think your text uses either of those. Certainly doesn't use a thing about homecoming. Oh, I'm almost certain I'm right, but I've got myself wigged out. If I'm wrong, put the truth in the comments and you can get another bonus point. So when we say that light is, the energy is quantized, it means it is broken into discrete amounts. And what this relates to is, it relates obviously to light, but we're going to also talk about it in terms of the electron. So we're going to come back to, as we be circling, we're going to circle back to the electron. Would you please tell me what kind of thing light is? We can think of light in two different ways. Okay, wave. What else? How else can we think of light? Particle. Very, very good. I thought I was going to have to pull your teeth a lot harder than that to get that out of you. Particle, singular. Also look at how I made my C. So when we think about light as a wave, we think about like any wave, that it has, I'm going to do this in black. This is review. We can indicate waves like this. What do we call this?
Transverse wave.
This type of symbology is used for a transverse wave most often, although it is also used sometimes for longitudinal waves. But we do see this most for a transverse wave, which light is a transverse wave. When we think about light as a wave, we think of it as a transverse wave. What do we call this that I drew, though, the line across there? Do you remember? This should be a review. I'm just asking you for vocab words about the baseline. Good, thank you. What's this? Nope.
That's the crest.
What's this? What is this measurement? Amplitude, A. What is the measurement from one point of one wave to the same point on the next wave? Wavelength indicated by the Greek letter lambda. Like half-life, both lambda and wavelength are represented by this Greek lowercase letter lambda. We're not dealing with those quantities at the same time, but we learned about half-life, or we reviewed half-life in the last lesson. In this one, we're talking about wavelength. So just be aware those are the same symbol, but we don't use them together that I'm aware of, and so it's okay. And then what do we measure as the amount of waves that go by in a certain amount of time? Frequency. And the inverse of frequency is period, which is capital T. Again, capital T could also be temperature, but in this context, it's always period. So frequency or inversely period. So this would be, just as a review, how many waves, usually per second, we'll put per unit of time, and this is how much time for one wave. So period is how much time for one wave. This quantity is period. And then frequency, although, check this out, scholars, in chemistry we usually use the Greek letter, oh, she done. We might have to turn the light on, Lucas. I should have charged that. I'm sorry. Go turn that on. We usually use the Greek letter nu for frequency. So this is frequency. Although we do still use the capital T for period. So frequency is the Greek letter nu. And how can we relate these quantities? Frequency, wavelength, and then we have another one called wave speed. How do we relate frequency and wavelength and wave speed? Yes, that's true. How do we relate them mathematically? How do we quantify them? Looking at this, how could we treat frequency, which is measured in per unit of time, and wavelength, which is usually measured in lengths, that's a wavelength, to get a wave speed?
How many wavelengths is per unit of time?
Yeah, well, not per, but time, so you're almost right. So we end up with the equation for light, c, which is the speed of light, equals lambda nu, where c is the speed of light, which you don't just have to have its units memorized, you can have its quantity memorized. The quantity of speed of light is 3.0 times 10 to the 8th meters per second. As we said, the lowercase lambda is wavelength. I'm going to put that it's measured in meters, although we very often use, especially for light, we use nanometers, which is billionths of a meter. But it's still fundamentally a meter. We just add prefixes to make the numbers easier to work with. And then nu, frequency, is measured in 1 over seconds, or an inverse second, which is seconds to the negative first power. Or we often abbreviate that as hertz. That's Hz for you scholars who can't read cursive. Hz, h lowercase h, lowercase z. No, 1 over s, 1 over seconds, right? The s is seconds. Or seconds to the negative first power, which is 1 over seconds, or we abbreviate it as hertz. So in this way, we can think of, this is the way in which we think of light as a wave. These are both done for. I'll do that later, whatever. I don't need to be filmed plugging in the lights. The wave nature of light tells us that light is continuous. The spectrum of light depends on its wavelength and frequency. By the way, when we talk about, this should be reviewed too, but when we talk about the electromagnetic spectrum, This is the many different kinds of light that exist, and they exist on a spectrum. Excuse me. In this, it's a Celsius. In this, if we increase in wavelength going this way, increase in wavelength, or which means we increase in frequency going the other way, what do we find here with the longest wavelength and the lowest frequency? You know what kind of light has the longest wavelength and the lowest frequency? You don't have to have these memorized, but you probably should or already do know them. Remember? It's radio. Radio waves. What next? Okay, I'll put gamma. It's way over here. It's the literal opposite. Okay, what else? So let's just do it that way. You tell me what you're thinking of, and if it exists, I'll put it on the spectrum for you. Microwave. There we go. Microwave is next. Is this still showing up on screen what I'm doing over here? Okay. UV, ultraviolet, above violet. So that goes here. Ultraviolet. I'm having a rough time with spelling. Ultraviolet, okay. There is something in between ultraviolet and gamma. Yep, you got it. Nice job. X-ray, okay. And there's one above microwave but below what we call the visible spectrum. Not ultraviolet, but now instead of above violet, it's below. No, yes, but it's directly below. No. If violet's on one end, the other end is, have you ever seen a rainbow? Red. Okay, so below red we would say infrared.
Oh, okay.
Like your goggles. So then within the visible light we have red, orange, yellow, green, blue, and then purple. I'm going to put pink, even though, well, we'll talk about pink at a different time. So that's within here, we call these visible light. Visible light. So the way that the different colors we see are because of the different wavelengths and frequencies of light. So what your eyes perceive as color is wavelength and frequency of light. Your eyes don't see these other ones, but they do see within that visible range. Okay, so now that should all, and it is all review, except for maybe this equation with the C in it and with these Greek letters you haven't seen before. But this should all be a review. In fact, it should be a review from 8th grade. But now when we talk about the particle nature of light, we call that, first of all, we call a particle of light the carrier of a discrete amount of energy, a photon. And it carries what we call a quantum of energy. A quantum is the lowest amount of something. A quantum comes from the Latin term for a counting stone. Like, like an abacus? You know an abacus? Have you ever heard of an abacus? Have you ever seen an abacus? So an abacus has a single thing that represents 1, and it can't be half of 1 or 2.5 or 2.33. It's 1 or 2. It's quantized. And so one quantum of energy carries the least amount of energy. This was one of your vocab words, but I'm going to tell it to you anyway. Least amount of energy physically possible. And a photon is the carrier of one of those. So one photon carries one quantum of energy. And so the energy of a photon or the energy of a quantum, right? Because a photon is the particle that carries one quantum of energy. This is a measurement of energy. This is a particle that carries that amount of energy. So we can measure them in the same way. What's up, Eliana? Yeah. Both of these are calculated by what we call Planck's constant, which is a fancy h, times the frequency of the light. So in both cases, capital E is energy, measured in what? What do we measure energy in the SI? Do you remember? No, that's frequency. Joules. Good. Planck's constant is, again, something that not just the unit we know, but the amount, the quantity of that unit. There's that word again. We call this Planck's constant, named after a man named Max Planck, a German. and it's 6.626 times 10 to the negative 34th joule seconds. Joule dot second. Is this a big number or a small number? Very, 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 very small. Literally, I told you it's the least amount of energy a thing can have. This is the smallest number in the universe, pretty much. Like, could I erase this and write to the negative 35th? Sure, but that doesn't relate to any measurable quantity. This does. It's effectively the smallest number in existence. This is the least amount of energy that an object can have. I shouldn't say object, but the least amount of energy that can be quantized, that can be thought of. And then nu is frequency again, measured in, what was frequency measured in? This is review from 4 minutes ago. Hertz, which is again seconds to the negative first power, or 1 over seconds. So now looking at, let's do our dimensional analysis. Let's analyze these dimensions. If this is inverse seconds, if this is seconds under 1, or 1 over seconds, and we multiply it by joules times seconds, what do we end up with for energy? In this equation, joule times seconds, if we multiply that by 1 over seconds, what do we get? You're all wrong. Just joules. The seconds reduced to 1. We're left with just joules. That's how we measure energy. I'm going to actually erase that because that's very basic algebra. I need more room over here. And so this is how we calculate the energy of a photon or the energy of a quantum. Knowing the frequency of light, we can calculate the energy that one photon of that light. And this is the duality. Duality. Duality is a concept in both philosophy and science in which something can be two things at once. Light can be understood to be a wave or a particle, but really wave and or particle. Like you can understand it both ways at once. And it gets much spookier than that. There are quantum mechanical experience. We call it quantum mechanics, by the way, because of the quantized energy. So if you've ever heard of someone tooting their own horn about how they know quantum mechanics, you do too now. Quantum mechanics just means analyzing light in a way, or really it's analyzing particles of an atom, the mechanics of an atom, in a way that uses the idea of light and quantized energy. But by the way, that quantum mechanics tells us that the light can exist in both ways at once, but when it's observed, it behaves in one way, and when it isn't observed, it behaves another way, which is a very spooky thing. It is like Schrodinger's cat, yeah. So the cat exists both as alive and dead at once, and that's kind of a thought experiment that is it's a metaphor for how we think about light as quantum mechanics. It's both, but neither, but also one or the other. Exactly right. Duality, if this were 3, it would be trinity, but it isn't. We're talking about 2 things, and so it's duality. So things existing as 2 at once. So I'm trying to think of another one. Like, are you a volleyball player or a Crawford High School student? Yeah, you are. You are. Okay. Is light a wave or a particle? Yes, it is a wave or a particle, and it is a wave and a particle. And what makes it now quantum mechanics is when we apply this to an electron. So electrons exist. You know, because we talked about it in the last lesson, that electrons are thought to exist in an electron cloud, right? Where instead of orbiting around an atom, although I'm going to draw that up here, we have the nucleus here, which we're not dealing with him anymore. See a nucleus. I mean, he still exists, but we think of it in this, what we call the Bohr model. And even though, I told you in the last lesson, that electrons are in a cloud and their motion is popping in and out of existence at random places, we oftentimes diagram them and still think of them in these quantized energy levels. So 1, 2, 3. N equals 1, 2, or 3. So, and only a certain number of electrons can exist in these energy levels at once, where N equals the energy level. Yeah, oh, of course you do. And the number of electrons that can exist in each is equal to 2n squared. So in the first energy level, how many electrons can there be? Well, let's do this math real quick. So we got, what's in the first energy level? Yes, so in the first energy level, how many electrons can there be? If it's energy level 1, what's 1? 1. Squared?
2. 1.
Thank you, Lucas. Let's all try again. Let's all try to channel a smart guy. And let's say, what would 1 squared be? 1 times 2? 2. So how many electrons in the first energy level? 2. Second energy level. Now we have 2 squared is 4 times 2 is 8. So the second energy level can have 8. What about the third energy level? What's 3 squared? 9 times 2 is 18. Good. So there can be 18 in the third energy level, and on and on and on. So the principal energy level, by the way, we sometimes call that the principal energy level, or we sometimes call it the quantum number. Those words are all more or less synonymous, is made up of different suborbitals. Oh, by the way, we also sometimes call it an orbital. So there's really 4 different terms for the same idea, that the electrons exist in certain energy levels, certain discrete discrete energy levels. So what I mean by discrete is that the electron can be in energy level 1 or 2, but not in between them. Okay, it can have energy level 1 or 2, but not in between. I'm not going to read my handwriting to you. What do you need, though?
What does that say?
Quantum number or orbital. So we can call these either energy levels, principal energy levels, quantum numbers, or orbitals, and they're all more or less synonymous. We use them. It's a little bit more nuanced than that, but at this level, they're all more or less synonymous, and they're made up of suborbitals. Sub meaning under. And the suborbitals have different shapes: S, P, D, and F. S is a sphere. P is a little like flowery dumbbell or a number 8 or an infinity sign. D is looking like a 4-leaf clover. And F is crazy. 2 concentric rings maybe with a clover inside of them. But you can see, what's the main change as we go across these? These are shapes of suborbitals. They get more complicated. Yeah, they get more loops. A really neat little idea about it is that just like, does anyone play guitar? Doesn't have to be guitar. Yes, you're right. Anyone does play guitar. Does anyone in this room play guitar? Do you really? Okay. Because I was going to say you're really betraying my wife if you play guitar and you haven't told us this whole time. But there's this neat picture that I like on page. Okay, on page 149, it's the harp. But this diagram of the harp and the strings shows, it's not showing up, who knows, maybe you'll see it, maybe you won't. The diagram of the harp is showing that as the string resonates with higher frequencies, there are more, like, right, you think of it, or like a jump rope, you think of it wobbling faster, eventually it'll get 2 nodes, and then if it wobbles even faster, it'll get 3. Same thing here. Higher frequency electrons, which, here, a fundamental thing that I missed, is that electrons also behave as a wave or a particle. So light behaves in this way, but so do electrons. And so the more energy electrons get, the more wiggling around they do. And the more wiggling around they do, the more they fill these shapes. Now, the main thing we're going to do, we're going to very briefly run over this in the video just so you can refer back to it, but the main way you're going to learn this is by doing, as you have already figured out, I hope. The main thing we're going to do here is we're going to apply these suborbital shapes to tell us the electron, what we call the electron configuration. This is going to break the world record for smallest amount of room anyone has ever taught electron configuration. Because this is actually a kind of, people do have difficulty with this, but as I said before, the main way you're going to learn this is by doing it. Electron configuration expresses the orbitals and suborbitals that electrons exist in the ground state of a certain atom. So let's do an easy one to begin with. We have beryllium here. You see beryllium? No. Everyone needs their periodic table out. You see beryllium? What is the atomic number of beryllium? 4. And so that means it has 4 electrons. That's true, but it means it has 4 protons. When it's neutral, that is in its ground state, which we sometimes call this, I'm going to put very small parentheses, ground state, electron configuration. When it's in its ground state, it has 4 electrons. And those 4 electrons exist in, well, we have principal energy level 1. The shape of the electrons in their suborbitals in principal energy level 1 is S. And in the first energy level, there are 2, so we put it like that. And then it also has a second energy level, 2, shape S with 2 more. Now, we're going to go over this in a second, but this number here, number 1, is the principal energy level. Principal energy level. I'll put LVL like we do in video games. S is the shape And this little baby number is how many there are. So we read these as 1s2, 2s2. And that's how we write electron configurations. And what that tells us is that there are 2 electrons in energy level 1. They're both in the S shape, right? And that there are 2 electrons in energy level 2, and they're both also in the S shape. Can you guess what other letters might be available to us here instead of S? Well, yeah, but what other ones might there be in some elements? P, D, and F. And now if I could rotate the camera, I would, but I will never get it back. You can see I have blocked out here. These are called blocks on the periodic table. These ones will all end in S. The last thing there will be an S. So something, S, something. These ones in the middle will all end in D. That's why I put D there. These ones over here will all end in P. Sorry, Eli. And then these ones down here will all end in F. Okay? That doesn't mean there's only going to have Fs or only Ds. And what we do is every time we go to the next element, we add how many electrons? Can you guess? 1, because we would add 1 proton. And so this was beryllium, 1s2, 2s2. If we went now to 5, which is boron, it would now be 2, which is, by the way, the energy level is the same as the period number. 2,
Oh, wow.
P, because now it's in the P block. And how many electrons will it get in that one? Just one little baby electron. So now this one is boron. 1s2, 2s2, 2p1 is boron. If we were going to go on and do carbon, it would be 1s2, 2s2, 2p.
What?
2. Good. Okay. Now if we were going to go on and do nitrogen, it would be 1s2, 2s2, 2p. 3. We just add 1 electron each time. But then you can see by the time we get to neon, we're adding 1 electron each time, we would go back and end it with 3s1 would be sodium. Yes, you will have these on the test. Yes, they will be more easy as you do more of them. And I'm trying to see if I'm forgetting one thing. I am forgetting one thing. If we have if we reach a noble gas, you know which ones are the noble gas, I hope. Okay, because that's review. No. Yeah, we do. And then you say the wrong one. Argon. No. Okay, so helium has a configuration of just 1s2. And so we can replace the part that is just like helium with this in brackets. We can say we just put helium in brackets. So that means it's the same as helium up till this point, and then we add these on to the back. And that's called the noble gas notation. We will do more of those as we go. The basic principle is you add 1 more electron each time. When you get to a new shape, you start adding them, and when you get to a new energy level, which, hold on, I've been wanting to do this for years. I'll just do it, just by default. These are the period numbers: 1, 2, 3, 4, 5, 6, 7, 6, 7. Well, 6 and 7, these just get shoved in here, you know. So this is not always the same as the principal energy level, but for the S and P's it is. The D's are 1 less and the F's are 2 less. There's a lot of little tricks that I'll teach you as we go along and as we're working on these, but for now, do you have questions about not how to do these, because you don't know yet, we will do it together, but do you have questions about how you would read an electron configuration, what these numbers mean? What's the big number mean? You should, because I just told you. No, the letter is a shape. Principal energy level. The big number is the principal energy level, which corresponds to which orbital it's in, right? Those little guys are the orbitals. What does this letter represent? The shape of the suborbital. And the little baby number? How many electrons there are in there. Yep. P's can hold, S's can hold 2, P's can hold 6, D's can hold 10, and F's can hold 14. Do you have questions about the dual nature of either electrons or light? Both of those can exist as either particles or waves. And this is the most nutshell of quantum mechanics that has ever existed, because this is quantum mechanics. And you got it in, well, like 25 minutes. What?